So this is my video for standard 5.1. I chose the problem that asks us to calculate the probability of measuring a state vector corresponding to a particle in an infinite box in its first three energy eigenstates. So what we'll do first, since the book gives us what each energy eigenstate is in terms of n, we can calculate the probability of measuring the nth energy eigenstate and then plug in for 1, 2, and 3. So that's what we do. So we know that probability of measuring the nth eigenstate within 3/4 to the end of the box is this integral of, because that eigenstate vector essentially corresponds to a probability density of finding the state in that energy eigenstate. So what we can do is add up the modulus squared over that interval, and that is what we do. So since we know that the nth eigenstate takes this form, we can calculate this integral, and we know that the modulus, since this is all real, we know that the modulus squared of this is just itself squared. So we get the integral from 3/4 L to L of 2 over L sine squared n pi x over L. And then to do this integral, we make a little use substitution for n pi x over L. And then when we do that, we get the integral of sine squared. And continuing on, we evaluate the integral using fundamental theorem of calculus. Then, after all the dust is settled, we get the probability of measuring the nth energy eigenstate in that interval of the infinite box is 1/4 minus 1 over n pi sine of n pi cosine of n pi plus sine of 3n pi over 4 cosine of 3n pi over 4. And this is what we would expect, because the energy eigenstates only depend on n. Then the probability of measuring each one should only depend on n also. So therefore, plugging in for 1, 2, and 3, the probabilities of measuring the first, second, and third eigenstates are this. Okay, and that is it for this video.